The last reaction we're going to cover this chapter will be the Baeyer-Villiger oxidation. In this case, we're going to take a ketone, must be a ketone, react it with a peroxy acid, and we're going to end up with an ester. We can take a look at the mechanism for a generic ketone. For an aldehyde, by the way, as I start writing this, aldehydes will simply be oxidized to carboxylic acids. If you throw a strong oxidizing agent like a peroxy acid with an aldehyde, you're just going to get a carboxylic acid out. So just like before, remember, if you took a primary alcohol and treated it with a strong oxidizing agent, you don't go to the aldehyde, you go directly to the carboxylic acid. It's the same idea here. So for ketones specifically, we can go ahead and take a look at the peroxy acid. We're going to have that oxygen go ahead and attack as a nucleophile. We end up opening up our ketone. And I'm going to actually draw this one, if you'll allow me. I'm going to draw it a little bit. I'm going to invert that. So we can have the minus charge down there. We'll have our R group pointing up. And now we have all these lovely oxygens. And so with this, we have our H here as well. That's still on our oxygen, which can then be attacked by it's actually going to be attacked by the carboxylic acid ketone, or carbonyl. Pops that open. And in doing so, we end up with now our alkoxide. We have the rest of the oxygens. We have now our protonated carboxylic acid carbonyl. And this is where the weird stuff happens. So doing this, we're going to end up closing down our alkoxide. We don't necessarily have a leaving group per se, but what's going to actually happen is one of our R groups is going to not leave, but it's going to migrate onto the oxygen. And the OO bond, which is particularly weak, will break. And in doing this, that's the driving force, by the way. We don't normally see R's migrating around. We have methide shifts and that sort of thing with carbon cations, but typically not commonly seen. But in doing so, with this, we see that we have that OO bond, which is particularly weak. We can take advantage of that, and we're going to end up migrating our R group onto that new oxygen, and we produce a carboxylic acid out at the other end. Just a plain old carboxylic acid. After it does some, technically, yeah, it's going to have to, instead of forming the minus charge there, yeah, we're probably going to end up just kicking the electrons all the way down to that that positive charge down there. In either case, we don't really care about the carboxylic acid side of things. The point is we end up migrating our R group. And we have considerations here. We're going to see that when we have asymmetrical ketones, we can decide which one is going to get the oxygen. For example, if we had a tertiary carbon versus a secondary carbon, we see that in the case of doing the Baeyer-Villiger oxidation here, we will end up oxidizing on the side that has the tertiary carbon. And we'll see that we can establish a trend here. So a tertiary carbon will migrate more easily than a secondary, which migrates more easily than phenyl. We're not reading that methyl, which migrates more easily than primary carbons. So that's the preference for oxidation if you have an asymmetrical ketone. So you'll always oxidize the side that follows this trend. The tertiary one will be preferentially oxidized over a secondary or anything else. A secondary will prefer to be oxidized over a primary carbon, and so on and so forth. So for example, if you have, of course, in aldehyde, by the way, I've said it already, but remember this just oxidizes to the carboxylic acid. So, not very exciting. But if we had something like this, where we have let's have a phenyl group next to a primary one. Phenyl takes priority over primary according to our list of reactivities here, or our migration capability. And so we end up actually now making the phenyl ester of this. So we'll end up inserting our oxygen on the benzene side. So, interesting reaction. We can do all sorts of fun stuff with it. Synthetically pretty useful, still used. But that's the last one for us. So one specifically for ketones now. In kind of our last warm-up, or our last thoughts about this, there's a lot of reactions we've seen in which we have various nucleophiles attacking these ketones or aldehydes. There's a lot to keep up with. So in kind of our next set of videos, we will talk a little bit about synthetic techniques and how to balance all these, because there are a lot, they all form different things, but it's just also showing you how synthetically useful aldehydes and ketones are. And so hopefully you'll have a little bit of an appreciation for them as you learn to hate them in practicing these reactions. Our next chapter will be on carboxylic acids and carboxylic acid derivatives. So we'll be continuing our carbonyl trends, focusing on molecules that have that C-double-O bond.